as soon as I know it's calling up.
I went through the paragraphs. Had some fun accuracy here.
Is this the right microphone right here? Is this is the right one? Okay, yeah.
And I went through some stuff that compared
Okay, where were you last time?
So you said the maximum
It's all right.
I actually looked into it.
Set those things so that you get
It looks like it's not the right time. It's on the video.
Well, I didn't call her out. I just asked Erica where.
No, Eric told me this.
Any questions about anything before we start? Questions? Just a warning that I'm going to be floating that message about homework 7 very shortly. Like, if you have any in, please tell me, because homework 8 is going to appear shortly. Or no, homework 9 is going to appear shortly. Right, that's correct. And that one, the drop dead date for that one is going to be before prelim 2, because I want to have the material on that homework for prelim 2. So if you're behind, please try to catch up. All right. Prelim 2 is the Wednesday before the week of Thanksgiving. So it's like Wednesday the something-teenth. 18th, yeah. Yeah, it's a while, but you know.
No, that's what you think right now, but.
Okay, so just be forewarned. Anyway, so last time we had these two very important versions of the Shannon-Nyquist sample theorem. And I'm not going to repeat them today, but essentially what it colloquially is that if you have a band-limited continuous time signal and you sample it faster than twice the bandwidth, then from those samples you can in principle reconstruct the whole signal. That's version 1. And version 2 is for any discrete time signal that has a DTFT, no matter where it came from. It didn't have to come from sampling originally, but any discrete time signal, there's a unique interpolation of that signal, T interpolation, for any T greater than 0 that's band limited within pi over T. And we call that X sub R. And so here's a picture, it's an important picture. And it goes like this. XC goes into a T sampler, and out of that T sampler comes a signal X, so X of n is going to be X of C of nt for all n in the integers. And if you put that through a sinc function, T interpolator, which for those of you who were around last spring in EC 2200, that's what we call a magic box. That's what we call the ideal D to C converter. What comes out of that is a signal XR. And sometimes XR is equal to XC. Sometimes it's not. And this is sort of a picture that has to do with the movies. Film a movie is look at a continuous time signal X of C and take a frame every 1/24th of a second, unless you're doing the Hobbit thing that Ian told me about last time. The interesting story is that they made this high frequency 60 frame per second or minute or whatever version of the Hobbit that people found disconcerting because somehow we're used to watching movies at 24 frames a second. I haven't read the articles yet, but it's pretty interesting. But anyway, this is what happens. You film a movie, right? T equals 1/24th. In that case, you get a sequence of still pictures. Those are the frames. And then when you watch the movie, I claim, so what you're doing is putting it through some kind of interpolation. And the question mark is here, is it a sinc function interpolation in the sense that you're putting it through? So this picture I want to look at in the context of a specific example. And this is one of the movie examples we talked about last spring, and it's just the classic thing. So here's a specific example. And what I'm going to do here is I'm going to model a spinning wheel that's spinning clockwise. So model a wheel turning clockwise, f0 revolutions per second as the signal, xc with specification xc of t equals e to the j 2 pi f0t, and if you abbreviate f0 as omega 0, that's going to be e to the j omega 0 t for all t. And model a wheel turning counterclockwise at f0 revs per second as the same thing, except with a minus sign in the x bar. So counterclockwise at, say, f1 frames, or f1's revs per second, is going to be modeled by the continuous time signal xc of t is equal to e to the minus j 2 pi f1t for all t. So if you see, and here, the way I've defined this f0 and f1, it's automatically a non-negative thing. How many revs per second? You can't say, well, it's spinning minus 20 revs per second. Whatever. Okay, so think of a wheel turning that way, and think if you have a movie of a wheel. So if you film a spinning wheel at 24 frames per second, that corresponds with t equals 1/24th of a second. And the wheel has some kind of radial marking or markings on it so that you can tell its orientation. So the wheel is equipped with a radial marking that shows its orientation. Various sequences of frames can arise. Now I'm going to look at one specific example. And which sequence of frames arises depends on the rate the wheel is turning. Okay, so specific example, let's say f0 is 18 revs per second. And assume the wheel spins clockwise. Okay, so 18 revs per second is 3/4 of a rev every 1/24th of a second. So this is the same as 3/4 of a rev clockwise every 1/24th of a second. And that's the interval between frames, and so the sequence of frames looks like this. Say the frame at time 0 has the radial marking pointing straight up, then the frame at time 1 is going to have the radial marking pointing this way, because between frame 0 and frame 1 it travels 3/4 of the way around. The frame at time 2, this travels 3/4 of the way around, pointing straight down. then it travels 3/4 of the way around, and it points this way, then it travels 3/4 of the way around and points straight up again. So you see this sequence of frames going on, and so on. Now if you see those frames in order, so this is going to be the frame at time n equals 0, n equals 1, n equals 2, which is the same as t equals 0, t equals 1/24 of a second, t equals 2/24 of a second, and so on. It looks like, when you watch the movie, it looks like the wheel, instead of spinning 3/4 of a rev clockwise every 1/24 of a second, or 18 revs per second clockwise, it looks as if it's spinning 1/4 of a rev counterclockwise every frame. So when you watch the movie, you quote unquote see the wheel turning 1/4 of a rev counterclockwise per frame. And I'm putting the word see in quotes. Because see isn't just what's happening in your eyes. See is what's happening in your eyes, what happens in your optic nerve, what happens in the vision systems in your brain, and all that kind of stuff. So you see the wheel turning 1/4 of a rev counterclockwise per frame, which is the same as 6 revs clockwise, or counterclockwise per second. Okay, so in terms of the signal models for spinning wheels, in terms of complex exponentials, if you film xc of t equal to e to the j 2 pi 18 t, sample at every t equals 1/24th, you see this signal that I'll call y of t, which is e to the minus j 2 pi 6t, when you watch it. Okay, so what I want to do is I want to reconcile this, which is basically just about how we see things when we watch a movie, with that picture up there. I want to show you that this y is in fact xr in the picture up there. In fact, what you see is the single function interpolation of what was filmed. Sample at the appropriate sampling rate. So it turns out that y equals x of r. That is to say, when you watch the movie, you come up with x of r as the explanation for the frame, for the frames you see. So your mind / vision system, quote unquote, explains the movie as x of r. And last time I was saying why I think this is kind of cool is that, to me, there's no reason a priori why the human vision system and brain should come up with that particular explanation for the frames. There's zillions of ways of interpolating between those frames. But we come up with the uniform, lowest bandwidth in some sense explanation. Why do we do that? I don't know. Creativity. Okay, now why does y equal x of r? Let's see how this happens. So to see this, what we're going to do is we're going to go through the whole sampling and interpolation apparatus. Okay. So xc of t is equal to e to the j 2 pi 18t. So let's write that as 36 pi t. Sample every t equals 1/24th of a second. okay, then you get your signal x of n. I'm not even going to write down what x of n is. I'm just going to look at the spectra. By the deconstruction equation, d, I can write down a formula for the dTft of x. X hat of little omega is equal to the sum over all k of 1 over t xc hat of little omega over t plus k 2 pi over t for all omega. What is the continuous time Fourier transform of a pure complex exponential? Say it louder, whoever said it. What is xc hat of capital Omega for this example? What? Somebody must know. Yeah, it's a delta function. Where? Well, at 36 pi. Xc hat of omega is 2 pi delta of omega minus 36 pi. Right? That's what you're supposed to know right away, that deltas in frequency correspond to pure complex exponentials, including constant function 1. So when I plug that into that equation and also plug in t equals 1/24, I get x hat of omega, little omega equals sum from a equals minus infinity to infinity, 24 times that thing evaluated at omega over t, so it's going to be 2 pi delta of 24 little omega plus k2 pi over t, which is 48 pi for all omega in reals. Now, it's tricky to deal with deltas when you scale the arguments, and there's going to be a homework problem that shows you how to do that. But it turns out that this is an impulse train that has an impulse everywhere. For each k, there's going to be one single value for which the argument is 0. And that is the value where that impulse is. And I'm not going to graph this or anything like that, but it has impulses at integer multiples of... Actually, there's a missing 36 pi somewhere. Hang on a second. There. Plus 48 pi k. That's what it is. Sorry, I was missing the 36 pi. There's an impulse you start at 36 pi in little omega space and you go to the right by any integer multiple of 24 pi, to the left by integer multiple of 24 pi, and there's going to be an impulse there. I'm not going to graph that picture because we're just going to undo that transformation in a moment. Okay, now what about xr hat? xr hat of capital Omega is equal to, this is from last time, t x hat of capital Omega times t when omega is less than or equal to pi over t, and 0 when omega is bigger than pi over t. That's from last time. So what we have to do now is just essentially unwrap the transformation we just did. And we have to figure out what x hat of omega t looks like when omega is less than or equal to pi over t. Okay. So x hat of omega has impulses at 36 pi plus k cubed pi for all k in the integers. So there's one at, say, 36 pi. There's one at 38, or k times 24. I always forget the 24. 48 pi. There's one at minus 12 pi. There's one at 36 plus 48 is 84 pi. And 36 minus 96 is minus 60 pi, etc. Right? Fair enough? No, I'm doing this wrong. This is terrible. This is terrible. I'm sorry about this. Let's erase that. Okay, take a deep breath into the camera. Oh, you actually are erasing. That's cool. So you take notes in pencil.
Yeah.
Excellent. Do you have a Stettler eraser? One of those fine German erasers that...
This is big.
Stettler erasers are really good. They're those white ones in the blue. Yeah, even the cameraman agrees. Yeah, they never dry out. They're like pink erasers always turn into a rock after a while. You know.
I'm actually using them right now.
Yeah. Okay. All right. So let's start this over again. This is what XR hat of omega is. It's T x hat of omega T. So let's just unwrap the transformation and then we'll figure out what the impulses are. Okay. Thus, XR hat of capital omega is equal to, just plug in T x hat of omega T. T is 1/24. That cancels the 24. Omega times capital T cancels the 24 in front of the omega. So it becomes sum from k equals minus infinity to infinity of 2 pi delta of capital omega minus 36 pi plus 48 pi k when omega is less than or equal to pi over t. What is pi over t? It's 24 pi. And it's 0 when omega is bigger than that. Okay, now let's look at where impulses happen. This is the easy thing. Where are the impulses in this infinite sum? That has impulses at 36 pi, 36 minus 48 pi, which is minus 12 pi, 36 plus 48 pi, which is, again, 84 pi, 36 minus 96 pi, which is minus 60 pi, etc. And all of them have weight 2 pi. So let's draw a picture of it, just for completeness' sake. Completeness' sake. The cool thing about this weather, by the way, to me, the incongruity is, by the way, those who are watching at home in a distant year, it's actually the 3rd of November and it's like 73 Fahrenheit outside. Okay? Now that's pretty good. How does that, and what's incongruous about that is it's not supposed to be this warm when the sun is this low in the sky. Okay, so you're walking and say, what's weird about it? Oh, that's it. Because if you think about it, the sun is this low in the sky, right around the end of January, also, which is like the coldest week of the year in general. So that's what's weird about it, I think. I'm convinced that that's why. Yeah. Do you guys, how many people have taken Bruce Longer's oceanography course? Or plan to? No one? You? One? Oh, you're in it? Okay. So we have two out of 70 or 81. No, I just saw him at CTV, and so I thought, oh, I wonder if anybody in my class is taking oceanography. Anyway, back to this. The infinite above has impulses in those places. Let's draw a picture. So if this is 24 pi, this is going to be 48 pi. So it's going to have an impulse here, and it has an impulse. This is minus 24 pi. Impulse here, 6 pi. Has an impulse at, so this is 48, 72, and then 6, 4 pi here, and so on. But XR hat of omega only equals that infinite sum, and let's put another one in this group. 48. X hat R of omega only equals that infinite sum of impulses when omega is less than or equal to 24 pi. Outside of 24 pi, it's 0. So that means that this is what XR hat of omega looks like. It's just this. It's just the impulse at minus 6 pi. And nothing else. And these are all way 2 pi away. i.e., x r hat of omega is equal to 2 pi delta of omega plus 6 pi. Steve?
That's supposed to be at minus 12. Minus 12 pi, yeah. Minus 12 pi.
Yeah, oh yeah, minus 12 pi, right. So, sorry. Yeah, put that in correctly. I'm jumping the gun here, and you can probably. So that's what XR hat of omega is. It's that. And so what's XR of t? XR of t is just the inverse Fourier transform of that. XRT is equal to e to the minus j 12 pi t. Okay? And that's the same as e to the minus j 2 pi times 6t. Right? And that's the same as, quote, 6 revs per second counterclockwise. So, up there I said you film xc of t equals e to the j2 pi att, every t equals 1/24 per second. You see y of t equals e to the minus j 12 pi t, or e to the minus j2 pi times 6t. And here we've shown mathematically that the sinc function interpolation of the frames is what you see. Okay. So the bottom line is this. For whatever reason, what we see is the sinc function interpolation of the frames. And remember last time I attached all these sort of weighty adjectives to interpolation. So sinc function / lowest bandwidth slash, quote unquote, preferred, whatever, or special interpolation of the frames. Why? Why do we see the lowest bandwidth? Why don't we sort of reconstruct things in a complicated way? And you could argue that this is the most parsimonious explanation for the frames. If your mind sort of automatically assumes the wheel is rotating at a uniform speed, then the most parsimonious, the sort of shortest explanation is the lowest bandwidth explanation. And one could argue that evolutionarily it's a good thing to come up with simple explanations. That if you came up with complicated explanations back in the caveman days, cave person days, I'm sorry, then you would have gotten killed and therefore not reproduced. You know, like if you see something that looks like a lion outside of your cave, you don't think, oh, that's Barney dressed up as a lion. You know, right? You think, oh, that's a lion. You know, that's the parsimonious explanation. And so the people who come up with parsimonious explanations are the ones who reproduce, and therefore that's why we see it. We could argue that. Or you could argue there's something about the human brain that has bandwidth. I don't know. I don't know that that's a fact. And why do we care about frequency? Why do we care about frequency content? That's another thing. Why do we have Fourier analysis? Were we compelled to find that? Because if you think about it, it turns out if you unwrap the cochlea in your ear, it's topologically a linear thing with a bunch of hairs in it of different thicknesses that react to different frequencies. So in some sense, when you put a sound into the ear, the cochlea exhibits the Fourier transform of the sound in terms of the amplitudes of the oscillations of the hairs. Does that mean that physiologically humans are cursed or blessed, however you want to look at it, or neither? It could be a content neutral thing, with thinking about the world in terms of frequency content. I don't know the answer to that one either. All these questions I think are good, and I never see these in DSP books or anything, so that's why I put them in the monograph. And you can mock them if you wish, but I don't think they're trivial questions. You know. Anyway, so does everybody get this? Like, see what I'm trying to say here? Why I think it's profound that there is a technical way of thinking about specially interpolating samples, and it turns out to be the way that we interpolate samples when we see a film. Anyway, okay, so there's that. That's one thing. And there's going to be some homework problems on this where, you know, and there's a little bit of terminology that goes along with this, okay? Remember last time when we were looking at forming using the deconstruction equation to figure out the DTFT of the sample signal, I said, in one picture we say aliasing occurs, and in the other picture no aliasing occurs. And what I want to do now is just talk very briefly about the A word, aliasing, where that comes up. Okay, so what happens in this case, in this example, what is our sampling frequency? Our sampling frequency is omega s equals 2 pi times 24, which is 48 pi. And the signal has bandwidth what? Not bandwidth. It's bandwidth. Omega m star equals 36 pi. Right, because it's 2 pi times 18. And clearly 48 is not bigger than twice the bandwidth. So since 48 pi is not bigger than 2 omega m star, which is 72 pi, we say that quote-unquote aliasing occurs. Why do we call aliasing? The idea here is that the original signal, the e to the j pi, j2 pi 18t, original signal xc of t equals e to the j 36 pi t is posing as x of t or y of t as xr of t. It's multiplication e to the minus j 2 pi times, so it's 12 pi t. That is to say, the original signal is assuming the alias that. Yeah.
Wait, is that statement true? 48 pi is greater than 72 pi?
It's not greater.
Oh, okay. Wait.
Is this? Do you prefer this?
I did not see that.
Greater with a circle and a.
Oh yeah, that's better.
That's better.
Yeah. I did not.
What's the international symbol for not greater than?
Plus 10 or equal to.
I just didn't want to write out the words. Does not exceed plus, blah blah blah.
Okay, like I just didn't see the slash.
Didn't see the slash. Yeah. Okay, so the thing is, the idea is that through the sampling process and the sync function interpolation process, the original continuous time signal poses as this signal here. It assumes the alias. So e to the j 36 pi t, quote unquote, assumes the alias e to the minus j 12 pi t. So that's where the word aliasing comes from, and why they use the word alias. And terminology we associate with this when we're sampling pure exponentials. Okay. So note that if you sample any pure complex exponential, say xc of t equals e to the j omega 0 t for all t at sampling frequency say omega s equals 2 pi over t. So there's every capital T, you take a sample, so the angular sampling frequency is 2 pi over t. Depending on the relationship of omega 0 and omega s, when you process those samples through the recovery process, you may or may not get xc back. So what you get when you process the samples through a sync function interpolator, and let me just use that as a verb. When you sync function interpolate the samples, it is always going to be a pure complex exponential sinusoid. It always takes the form x sub r of t is equal to e to the j, say, omega 1t for some omega 1. What's that omega 1 going to be? Omega 1 is going to be the unique frequency in the interval minus pi over t to pi over t. So unique value in the interval minus pi over t up to pi over t that is an integer translate by 2 pi over t of omega 0. So that's of the form 2 pi over t, or it's omega 0 plus n 2 pi over t for some integer n, positive, negative, whatever. And this, by the way, assumes that we're ignoring the borderline case for now. And there's going to be a homework problem in this case. We're ignoring the borderline case where omega 0 is an odd multiple of pi. Of pi over t. Now, why is there only one value of the form omega 0 plus n times 2 pi over t in the interval minus pi over t under this assumption? If you look at what omega 0 is, all of the signals that give rise to the same samples are going to be of the form. So here's the idea. Every signal that gives rise to the same t-sample x, and let's say every sinusoid gives rise to the same t-sample x as x sub c does, is of the form e to the j omega 0 plus some integer multiple of 2 pi over t times t. Which is the same as e to the j omega 0 plus m omega s t. Where omega s is the angular sampling frequency. These signals are called the aliases of the continuous time aliases of x sub c. This is what we call them last spring, at least, the continuous time aliases of x sub c with respect to the sampling rate or interval t, capital T, and the one whose frequency is in that inner interval minus pi over t to pi over t and I'm going to make this an open interval because really it can't be a closed interval. It has to be in the open interval if that boundary case is out. The one with frequency omega 1 in there is called the principal continuous time alias. Of x sub c with respect to the sampling interval t. So if you take a pure sinusoid, you put it through the two boxes, the filming box, or whatever, and the movie watching box. So So when x of c of t is e to the j negative 0 t for all t, if you put xc into the t sampler, to yield discrete time signal x, and put that into a sync function t interpolator, what comes out is the signal xr, and xr is going to be the principal continuous time alias of xc with respect to the sampling interval capital T. So this is a little shortcut for finding xr. We don't have to go through all that delta stuff that we did before. In the special case where xr is a pure sinusoid, or xc is a pure sinusoid. Is everyone familiar with WRT as with respect to? Yeah? Anybody read David Foster Wallace essays or anything? Yeah? Yeah? No? Okay. He uses that all the time. All right. With respect to t. So you can think of this as a shortcut for solving problems involving only pure sinusoids. Okay. And here's an interesting thing. Like, what this one thing among others that it says is the following. That if I take samples of a pure sinusoid and sync function interpolate them, I'm always going to get a pure sinusoid. That's a little surprising, I think. But anyway. All right. So there. So that's sampling stuff. Now, there's one more thing I want to talk about that's sampling related, and that's the idea of pulse sampling and time division multiplexing. And this is something that's of great practical interest. And on the board when we came in, maybe it's from Bruce Lannon, I'm not sure, but it looked as if he was talking about something called ADPCM, adaptive differential pulse code modulation. This is actually related to this time division multiplexing that we're going to talk about. And this won't take very long. It'll take longer than 3 minutes, which is about what we have left. But I want to introduce some notation so we can move on. So here's the final sampling related topic. And that is pulse sampling and time division multiplexing. Okay. First, some notation. If I'm given capital T bigger than 0 and A bigger than 0 with A much less than capital T, it doesn't have to be much less, but it has to be less than capital T over 2 at least, I'm going to define this is like a capital pi, sort of. That's going to be the notation for this. And you'll sort of see why I call it that, of t. As follows. It's the sum from n equals minus infinity to infinity of p sub a of t minus n times capital T. All t in the reals. What is that? That is a pulse train. So if we graph it versus t, it has a pulse of width a centered at t equals 0, a pulse of width a centered at t equals cap t, one at t equals cap 2t, and so on. And then there's one over here at minus t, and so on in that direction. These all have height 1, and they all have width a. And this is a pulse train, as opposed to an impulse train that we've seen before. This is an actual signal, and it's a decent signal. And what we're going to end up doing is we're going to multiply a signal x by this and get something that's not quite a sampled version of X. It has little pieces of X, and that's what we call a pulse sampled version of X. And we're going to play around with those a little bit. So just have to save that up for tomorrow, I guess. And again, I actually brought the stuff today, so if you want to pick up your prelim that you haven't picked up yet, or homeworks 1, 2, or 3, I have them all up here.